Right now, inside every atom in your body sits a tiny particle called a proton. Weigh it, and something breaks. Inside are 3 tiny quarks. Add up their weight, and you get about 1% of the proton. 1%. The other 99% comes from somewhere the quarks cannot explain. You've heard the answer before. The Higgs gives things their mass. But for the proton, the Higgs barely counts. So we're going hunting. Down into a space smaller than a speck of dust, past quarks moving near the speed of light, through a boiling storm of pure energy to the real source of your weight. If a mystery this big excites you, hit like and subscribe now. The heaviest thing about you might turn out to be almost nothing at all. Let's find out why. Prepare yourselves. Look at your hand. Right now it feels solid. Bone, skin, warmth. But zoom in close enough past the skin, past the cells, past the atoms, and you reach a tiny ball sitting at the center of everything. That ball is a proton, and it is about to break the rules of what you think weight even means. Every atom in the universe has at least one. Hydrogen, the simplest atom of all, is basically one proton with one tiny electron zipping around it. Your body holds more protons than there are grains of sand on every beach on Earth. Way more. Try to picture that number and your brain just gives up. So the proton is small. How small? Shrink one atom until it fills a football stadium. In that giant stadium, the proton at the center would be about the size of a marble sitting on the 50-yard line. Everything else, the whole roaring stadium of space, sits nearly empty. The marble in the middle holds almost all the weight. That marble is where your story lives. Almost everything heavy about you, your bones, your muscles, the water in your blood, traces back to these little cores hiding inside your atoms. Lose the protons and you lose yourself. Here is where it gets strange. A proton only looks like a solid marble from far off. Get close, and it turns into one of the wildest places in the entire universe. A storm, a furnace, a blur of things moving so fast they barely seem to be there at all. Scientists have known protons exist for over 100 years. A physicist named Ernest Rutherford fired tiny bullets at a thin sheet of gold and watched some of them bounce straight back, like a marble bouncing off something hidden in fog. That bounce told him a hard, heavy center was buried inside every atom. He had found the proton, and it changed everything we thought we knew about matter. Finding the proton and understanding it turned out to be 2 very different things. Rutherford knew it was there. He knew it was heavy. What he could not have guessed is that the source of that heaviness would take another 100 years to uncover, and that the answer would sound almost impossible when it finally arrived. A proton has weight. We can measure it. We know the number exactly, and when you crack it open to find where that weight comes from, the pieces inside come nowhere close to adding up. It is like weighing a full backpack, opening it, finding it basically empty, and yet it still drags your shoulders down. Something inside that tiny ball is making weight out of what looks like nothing at all. Something that hides in a place far too small for your eyes to ever see, and to find it, we are going to shrink down and go inside, so hold that picture. A marble at the center of a stadium, a core so small it makes an atom look like empty air, yet so heavy it carries nearly all of you. Before we solve the mystery of where its weight comes from, we need one simple thing. We need to know exactly what a single proton weighs. That sounds easy. It even sounds boring. But that one number is the thread we pull, and once we pull it, the whole thing starts to unravel. You cannot weigh a proton on a kitchen scale. It is far too light for any scale you have ever touched. To match the weight of a single paperclip, you would need to line up around a billion protons. That is a 1 with 27 zeros trailing behind it. Written out, it would run right off the edge of your screen. So by everyday standards, a proton weighs almost nothing. Yet inside its own tiny world, it is a heavyweight champion. Sitting near every proton is a much smaller particle called the electron. The electron is the featherweight of the atom, whizzing around the outside edges. Line the 2 up and the proton weighs about 1,800 times more than the electron. Picture a full-grown horse standing next to a single feather. That gap is roughly the gap between them. The proton is the horse. The feather barely registers. Wait, this small forced physicist to invent a smarter way to talk about it. So they stopped using grams and started measuring the proton with energy instead. That choice sounds bizarre right now, and by the end of this journey you will see why it is perfect. For today, just hold on to one clean number. When scientists measure a proton in their special energy units, they get about 938. Say it out loud. 938. That number is the whole reason we are here. Why does one number matter so much? Because we can measure it with jaw-dropping accuracy. Scientists can pin down the weight of a proton to more decimal places than almost anything else in nature. They trap single protons in magnetic bottles and watch them spin, and from that spin they read the weight like reading a scale that never lies. This part is rock solid. Confirmed, no argument. So we have a heavy little core, and we know its weight down to a level of detail that would make your head spin. Everything so far feels safe, predictable, like science doing its normal job. Now comes the first crack. That number, 938, is supposed to come from the stuff inside the proton. That is how weight usually works. Weigh a lunchbox, and its weight is just the sandwich, plus the apple, plus the box. Add up the parts, and you get the whole, simple, fair, the way the world should behave. So physicists did the obvious thing. They looked inside the proton to find the parts. They wanted to add them up and watch the numbers land right on 938, proving they understood the little core completely. They found the parts, 3 of them, tiny and real, and when they weighed those 3 parts and added them together, the total came out horribly, laughably wrong. The pieces inside a proton do not sum to the weight of the proton. They fall short by a stunning amount, not by a little, by almost everything. That single failed sum broke open one of the deepest questions in all of physics. If the parts inside a proton do not carry its weight, then what does? Where is the heaviness actually hiding? And how can something be far heavier than the stuff it is made of? To even begin answering that, we have to meet the 3 tiny pieces locked inside, because they are the prime suspects, and their story is even stranger than the missing weight itself. Time to break a proton apart and see what falls out. For a long time, people thought the proton was the smallest thing there was, a tiny solid ball. End of story. Nothing smaller inside. That idea held for decades. Then, in the 1960s, scientists built machines that could punch straight through a proton and feel around inside it. These machines are called particle accelerators, and the big ones stretch for miles underground. They grab particles and whip them up to nearly the speed of a light, then smash them into protons and watch what sprays out. It is like firing a bullet through a wall to learn what the wall is made of, except the bullet is smaller than an atom and moving almost as fast as light itself. When they fired these bullets into protons, the bullets did not pass straight through. Sometimes they bounced hard, kicked off by tiny hard lumps buried deep inside. That bounce was the giveaway. The proton was hiding something, 3 somethings. Those 3 lumps got a strange name. Quarks. A physicist named Murray Gell-Mann picked the word out of a weird line in a novel, and somehow it stuck. Today, every scientist on Earth uses it. Quarks are real, confirmed, measured over and over. They are as real as the proton itself. A proton holds exactly 3 of them. 2 of one kind, called up quarks, and 1 of another kind, called a down quark. 2 up, 1 down. That mix is what makes a proton a proton. Change the recipe, and you get a different particle entirely. Now, quarks are almost impossibly small. If the proton were the size of that marble on the stadium field, the quarks inside would be like 3 tiny gnats buzzing around in all that space. The proton, which already looked mostly empty, turns out to be even emptier than you feared. 3 little specks, and a whole lot of room around them. So picture it. A proton is a tiny bubble, and inside float 3 quarks, buzzing and darting like trapped insects that can never escape. For now, just hold that picture. 3 specks in a bubble. It looks calm. It looks simple. It looks like we finally found the answer. Here is the trap. Those 3 quarks feel like the obvious source of the proton's weight. They are the solid bits, the hard lumps, the stuff you smash into. Any normal person would say the weight of the proton is just the weight of its 3 quarks added up. That is how weight works everywhere else in your life. So scientists went ahead and did that. They measured the weight of 1 up quark. They measured the weight of 1 down quark. Careful work, checked and rechecked, confirmed. Then they added 2 ups and 1 down together, expecting the total to march right up to that magic number, 938. The answer they got was not close. It was so far off that at first it looks like a mistake, like someone dropped a decimal point or forgot to carry a number. But there was no mistake. The math was clean, the measurements were solid, the 3 quarks inside a proton, the very things everyone assumed carried its weight, barely weigh anything at all. And when you finally see the size of that gap, it stops being a math problem and starts feeling like a hole in reality itself. Let us actually do the sum. 2 up quarks and 1 down quark. Add them up and see how close we get to 938. An up quark, measured in those same energy units, weighs about 2. Tiny. A down quark weighs a bit more, about 5. Also tiny. So we take 2 ups, that is 2 plus 2, and add 1 down, that is 5 more, 2 plus 2 plus 5. The 3 quarks inside a proton weigh about 9. Total. 9. Stop and let those 2 numbers sit side by side. The proton weighs about 938. The 3 quarks inside it weigh about 9. The parts add up to around 1% of the whole. 1%. To feel how insane that is, try it with something real. Imagine you step on a scale and it reads 100 pounds. Now imagine scientists open you up to find where that weight lives, and they discover your entire body, all your bones and muscles and blood, weighs only 1 single pound. The other 99 pounds come from somewhere they cannot point to. That is exactly the situation inside every proton in your body, right now. This is confirmed, rock solid, measured in labs around the world, checked by different teams using different machines, and they all land in the same impossible place. The quarks are real, their weight is real, and their weight is almost nothing compared to the proton they build. So the obvious answer, the one that felt so safe, just collapsed. The 3 quarks are not carrying the proton's weight. They cannot be. They are 99 times too light for the job. It would be like finding out a loaded 18-wheeler truck weighs the same as its 3-door handles. For a while, this drove physicists a little crazy. They had cracked the proton open, found its parts, weighed them, and the numbers refused to work. Something enormous was missing. 99% of everything was unaccounted for. That is not a rounding error you can shrug off. That is the vast majority of all the ordinary weight in the universe gone missing from the math. Think about what that really means for a second. Nearly all the weight of every atom, every rock, every ocean, every star, every living thing comes from a source that is not the quarks. The little pieces we can point to and name are almost weightless. The real heaviness is coming from something else, something hidden, something we have not met yet. And people wanted a fast, easy answer. They wanted a hero to swoop in and explain the missing 99% in one clean sentence. As it happens, there is a famous answer that almost everyone reaches for. You have probably heard it yourself. It has been on the news, in headlines, in classrooms. It sounds smart. It sounds final. It goes like this. There is a special thing in the universe that gives everything its mass, its weight. It even won a Nobel Prize. So surely that is the missing 99%, right? Mystery solved. Go home. That answer is wrong. For the proton, it is almost completely wrong. And understanding exactly why it fails is the moment this whole story flips from a simple weighing problem into something far stranger and far bigger than anyone expected. We have a hole, a 99% hole in the weight of everything. And before we hunt down what fills it, we need to feel how huge that hole truly is, because most people have no idea it even exists. Every day you trust that weight comes from stuff. Your backpack is heavy because of the books in it. A truck is heavy because of the metal. Add up the material, get the weight. This rule feels so obvious that breaking it seems illegal. The proton breaks it anyway. The proton is like a backpack that weighs 100 pounds while holding 1 pound of books. The books are the quarks. The other 99 pounds are made of something you cannot hold, cannot see, and at first cannot even name. Here is the part that should stop you cold. This is not some rare special particle in a distant lab. This is you. Your body is packed with protons and every one of them plays the same trick. So more than 99% of your body weight comes from this hidden source. Step on a scale. Almost none of that number is coming from the actual pieces you are built from. Let me say it as plainly as I can. If you weigh 100 pounds, only about 1 pound of that comes from the true weight of your quarks and electrons. The other 99 pounds are being generated inside your protons by a force, by energy, by motion. by something with no weight of its own that somehow creates almost all the weight there is. That idea sounds broken. Weight from weightlessness. Heaviness from nothing solid. It feels like being told a shadow can lift a car, and yet it is confirmed, measured, and true. This is one of the strangest facts in all of science, and hardly anyone outside of physics has ever heard it. So where is the hole? Where does the missing 99% live? It is not spread out in some new heavy particle we forgot to count. Scientists have looked. There is no secret heavy lump hiding in there. The 3 quarks really are the only solid pieces, and they really are almost weightless. The weight is coming from the space between them, from the invisible force that ties those 3 quarks together, from the frantic, blurring motion of the quarks as they race around inside their tiny prison. All of that, the force and the motion and the energy, is somehow being turned into weight. That is the whole mystery in one line. The proton is heavy because of what happens between its parts, and almost nothing to do with the parts themselves. To crack this, we have to understand a strange trade that happens deep inside matter. A trade where pure energy becomes solid weight, and where the fastest, most violent motion you can imagine gets frozen into something you can put on a scale. But first, we have to deal with that famous wrong answer, the one everyone gives, the one about a special mass-giving particle that supposedly explains all of this. Because until we prove why the answer fails, the real solution will never make sense. And the story of why the most famous idea in modern physics does almost nothing for the proton is a twist most people never see coming. Ask almost anyone where mass comes from and you will hear the same 3 words: the Higgs boson. A few years back, the Higgs boson was everywhere. Newspapers called it the God particle. Scientists at a giant machine in Europe spent billions of dollars and decades of work hunting for it. In 2012, they finally caught it, and the whole world cheered. The headlines all said the same thing. Scientists find the particle that gives everything its mass, so it seems open and shut. We have a proton missing 99% of its weight, and we have a famous particle whose entire job is handing out weight. Case closed. The Higgs must be the answer. That is what almost everyone believes, including plenty of smart people who should know better. That answer is wrong for the proton. Beautifully, cleanly wrong. And seeing why is like watching a magic trick get exposed. The Higgs is real, confirmed, it exists, and it truly does give mass to certain particles. That part of the story is solid gold. The trouble is what people think it means. When the headline said the Higgs gives everything its mass, they left out something enormous. The Higgs gives mass to the tiny fundamental particles like quarks and electrons, when those particles have any mass of their own to begin with. Remember the weight of the 3 quarks inside a proton? About 9 in our units. That little bit of weight, that 1%, is the part the Higgs is actually responsible for. The Higgs is the reason an up quark weighs about 2 and a down quark weighs about 5. Take the Higgs away and the quarks would weigh nothing at all. So the Higgs handles the quark weight. 2, 2, and 5. That famous Nobel Prize winning God particle takes care of about 9 out of 938, 1%. It is doing a real job, but a tiny one. The other 99%? The Higgs never touches it. The gluons, the force, the motion, the energy inside the proton, the Higgs, has nothing to do with any of that. It cannot fill the hole. It was never built to. Feel the size of that mix-up. The most famous idea in modern physics, the thing that made every front page, the reason a machine the size of a city got built under the ground, explains only 1% of your weight. The headlines were technically pointing at something true, then blew it up into a claim it could never support. So the God particle, the celebrated answer to where mass comes from, turns out to be almost a footnote when it comes to the weight of ordinary matter. The stuff you are made of, the protons in your bones, get nearly all their weight from a totally different place. A place with no famous name, no Nobel headlines, no city-sized machine built to celebrate it. That place is the real hero of this story, and it has been hiding in plain sight the entire time. To find it, we first have to be fair to the Higgs, and understand exactly what it does do, because the small job it performs is stranger and more important than it sounds. Without that 1%, everything else would fall apart in a way you would never expect. Let us give the Higgs a fair trial. It only explains 1% of the proton's weight true. But that 1% turns out to matter far more than its tiny size suggests, and understanding it clears the way to the real answer. Picture the whole universe filled with an invisible, sticky substance, not air, something deeper, spread through all of space, in every corner, in the room you're sitting in right now. Scientists call it the Higgs field. It has no colour, no smell, and you pass through it every second without noticing. Some particles feel this field and get slowed down by it, like a person trying to run through deep water. That drag is what we experience as mass. A particle that gets dragged a lot feels heavy. A particle that slides through cleanly feels light. The Higgs field is the water, the dragging is the weight. Different particles feel different amounts of drag. The down quark feels a bit more, so it weighs about 5. The up quark feels a bit less, so it weighs about 2. Electrons feel only a tiny pull, so they stay feather-light. And light itself, the photon, feels no pull at all, which is exactly why light can move at the fastest speed in the universe. It never gets dragged. So the Higgs field is real, and it does something genuine. It hands out the small, built-in weights of the tiniest particles. Confirmed by that giant European machine in 2012, checked and rechecked. This is not a guess anymore, it is settled science. Here is why that tiny 1% still deserves respect. That little bit of quark weight, handed out by the Higgs, is holding the universe together in a way you would never guess. It comes down to a razor-thin difference between two particles, and that difference is the reason atoms exist at all. Remember, a proton is 2 up quarks and 1 down quark. Its cousin, the neutron, is 1 up quark and 2 down quarks. The only difference is swapping an up for a down, and since the down quark is a touch heavier, the neutron ends up just barely heavier than the proton. A tiny gap. A whisker. That whisker set by the Higgs decides the fate of everything. Because of it, a lone neutron is slightly unstable, while a lone proton stays rock steady, seemingly forever. If the Higgs had made the up quark heavier instead of the down, the proton would fall apart and the neutron would win. Hydrogen could not exist. Water could not exist. Stars could not burn the way they do. You could not exist. So the Higgs plays a small role in the weight of the proton, but a giant role in whether a stable proton can even be. It sets the delicate balance that lets ordinary matter survive. 1% of the weight, 100% of the reason atoms hold together. Still, we came here for the missing 99% and the Higgs cannot give it to us. It has done its job and stepped aside. The huge hole in the proton's weight is still wide open, still unexplained, still waiting. To fill it, we have to leave the Higgs behind and meet the true source of your weight. It is a force so powerful, it makes gravity look like a gentle breeze, and it has been raging inside every proton in your body since the day you were born. There are 4 basic forces that run the entire universe. Gravity is the one you know, the pull that keeps your feet on the ground. Yet gravity is actually the weakest of the 4 by a shocking margin. The real muscle in the universe belongs to a force most people have never heard of, the strong force, and it is our prime suspect for the missing 99%. The strong force lives inside the proton. Its job is to grab the quarks and hold them together, and it does that job with a grip so fierce it barely makes sense. To feel how strong it is, compare it to gravity. If gravity were the weight of a single feather, the strong force would be the weight of a mountain sitting on top of it. That is not poetry. The strong force is trillions of times mightier than gravity inside that tiny space. Why does the proton even need a force this violent? Because the quarks inside carry a special property that makes them shove each other away. Hard. Left alone, the quarks would fly apart in an instant and the proton would blow itself to pieces. Something has to overpower that shoving and lock the quarks in place. The strong force is that something, and it wins the fight in every proton every moment without ever getting tired. Now here is the piece that turns a force into an answer. Holding those quarks together takes a colossal amount of energy. The strong force is straining constantly to keep 3 quarks that want to escape trapped in a space smaller than you can imagine. All that straining, all that effort, all that energy is packed into the tiny volume of the proton. And energy, it turns out, has weight. That is the secret. That is the whole trick. The energy locked inside the proton by the strong force is so vast that it becomes almost all of the proton's weight. The quarks are light. The force holding them is not light at all. It is heavy in a strange and real way, because the energy it carries counts as weight. To picture it, Imagine 3 wild dogs on 3 leashes, all pulling in different directions, straining as hard as they can. The dogs are the quarks, the leashes are the strong force. Now imagine those straining leashes were somehow so full of tension that the tension itself weighed more than 100 dogs. That is the proton. The leashes weigh far more than the animals they hold. This is confirmed. The strong force is real, measured, studied for decades, and awarded a Nobel Prize in 2004 for the scientists who cracked how it works. There is no doubt it exists or that it is monstrously powerful. The strong force is the true engine of your weight, running silently inside every proton in your body. But saying the strong force makes weight is like saying an engine makes a car move. It is true, and it is also not enough. We need to look under the hood. We need to see how a force with no solid parts, no little lumps of matter, actually stores enough energy to outweigh everything inside it 99-1. The answer lives in the messengers of the strong force, strange particles that carry the force between the quarks, that weigh nothing themselves, yet somehow hold the heaviest secret in ordinary matter. They are called gluons, and they are next. Meet the gluon. Its name says exactly what it does. It is the glue that holds the quarks together, and it may be the strangest player in this whole story. Every force in the universe is carried by a messenger particle. The messenger zips between things and delivers the push or the pull. For the strong force, that messenger is the gluon. Quarks fling gluons back and forth constantly, and every time a gluon passes between them, it yanks them tighter together. Trillions upon trillions of these tiny catches happen inside a single proton every instant. Here is the first shock about gluons. They weigh nothing. 0. A gluon has no mass of its own at all, just like a particle of light. You could gather up a whole crowd of gluons and your scale would still read 0. They are pure force carriers, weightless messengers, ghosts of the strong force. So now the puzzle sharpens to a fine point. The 3 quarks weigh almost nothing. The gluons weigh literally nothing. Add up every actual piece inside a proton, and you get close to 0 real weight. Yet the proton is heavy. 938. Where on earth is that number coming from if the parts all weigh nothing? The answer is one of the most beautiful ideas in all of science, and it hides inside the gluons themselves. A gluon has no weight, true, but a gluon flying between quarks carries energy. Lots of it. The space inside the proton is packed wall to wall with gluons, all buzzing, all carrying energy, all straining to keep the quarks locked down. That energy is real, and energy has a hidden connection to weight that we're about to unlock. Picture a rubber band stretched tight between your fingers. The rubber band itself is light, almost weightless. But when you stretch it, you fill it with energy. You can feel it pulling, straining, ready to snap back. Now imagine that stretched energy was so intense it actually made the rubber band heavier. That is what the gluon field does inside a proton. The gluons stretch between the quarks like countless tense rubber bands, and the energy in all that tension becomes weight. Gluons also do something no other force messenger dares to do, something that makes the strong force explode in power. But that is a shock for later, so hold it. For now, sit with this strange new picture of a proton, not 3 little balls sitting quietly. A raging, crowded storm of weightless gluons flying in every direction, quarks buzzing among them near the speed of light, and energy packed so densely into a space smaller than a speck of dust that it outweighs everything solid 100 times over. Almost none of the proton is stuff. Almost all of it is action, force in motion, energy on the boil, and somehow that boiling energy is what your bones and blood and every heavy thing about you are truly made of. We keep circling back to the same magic rule. Energy becomes weight. We have said it a few times now, and you might be wondering how that is even possible. How does something with no weight of its own turn into weight you can measure on a scale? The answer is the most famous equation in the history of science, and it works in a direction almost no one thinks about. You have seen the equation even if you never studied physics. 3 little symbols that change the world. E equals mc squared. It might be the most famous line ever written in science, printed on posters and shirts and mugs. But almost everyone reads it the wrong way around, and reading it the right way is the key that unlocks the whole proton mystery. Most people know this equation as the recipe for the atomic bomb, Take a tiny bit of mass, some heavy material, and turn it into a monstrous burst of energy. Mass in, energy out. That is the direction everyone learns. It is true, and it is terrifying, and it is only half the story. The equal sign in the middle works both ways. That is the part people miss. If mass can become energy, then energy can become mass. Run the equation backward. Pour energy in, and weight comes out. Einstein's famous line does not just say mass makes energy. It says mass and energy are two faces of the same coin. They are the same thing, wearing different costumes. Read it slowly. Energy and mass can turn into each other. A pile of pure energy with no solid matter in it at all weighs something. It has mass simply because it is energy. This is confirmed, tested countless times, one of the most solid facts in all of physics. Energy is heavy. Trapped energy sits on a scale and pushes down just like a rock. Now bring it home to the proton. Inside that tiny core, the strong force has packed in an unbelievable amount of energy. The straining gluons, the racing quarks, the boiling storm of force, all of that is energy, crammed into a space smaller than a dust speck. And by Einstein's equation running backward, that trapped energy becomes weight. That is the answer. That is where the missing 99% lives. It was never a hidden particle. It was never a secret heavy lump. It is pure energy, converted straight into mass by the most famous equation in science, working in the direction hardly anyone thinks about. To feel it, picture a sealed box with mirrors on the inside and a beam of light bouncing around inside it forever. Light has no weight, but trap enough light energy in that box, and the box itself would weigh a tiny bit more than an empty one. The bouncing light, pure weightless energy, adds real weight to the box. The proton is that box. The strong force is the trapped light. And the extra weight is almost all of you. So the truth of your body starts to come clear, and it is stranger than any story. You're mostly not made of stuff. You're made of trapped energy, frozen into the shape of matter by Einstein's equation. The heaviness of your bones is really the heaviness of energy, locked inside your protons and pretending to be solid. This one idea, energy becoming mass, is the beating heart of the entire mystery. Every strange thing left in this story flows from it. But knowing that energy becomes weight is one thing. Seeing exactly how the proton fills itself with that much energy is another. And the first source of it is hiding in the quarks themselves, moving so fast that their sheer motion turns into weight you can hold. We keep calling the quarks light, almost weightless, barely there. That is true when they sit still. The trouble is, the quarks inside a proton never ever sit still. They move. And how fast they move changes everything. Trapped inside their tiny bubble, squeezed by the strong force, the quarks race around at staggering speed, close to the speed of light. Light is the fastest thing in the universe, streaking around the whole Earth 7 times in 1 second. The quarks inside your protons are moving at nearly that speed forever, in a space so small it makes a grain of sand look like a planet. Here is why that matters, and it comes straight from Einstein again. When something moves, it carries energy. The faster it moves, the more energy it carries. This is called energy of motion, and you feel a version of it every day. A thrown baseball stings your hand because it carries energy of motion. A speeding car hits harder than a slow one for the same reason. Speed is energy. Now push that to the extreme. When a particle moves close to the speed of light, its energy of motion becomes gigantic, far larger than the tiny weight it had while sitting still. The quarks in a proton are doing exactly this. Their built-in weight is tiny, about 2 or 5 in our units, but their energy of motion, from racing near light speed, is enormous, many times larger than their resting weight. And remember the golden rule, energy becomes weight, so all that energy of motion, all that frantic racing turns into extra mass. The quarks weigh far more inside a speeding proton than they would sitting still, simply because they never stop moving. Their speed makes them heavy. Picture a hummingbird. At rest it weighs almost nothing, light as a feather. Now imagine a hummingbird that beats its wings so fast and darts so quickly that the pure energy of its motion made it weigh as much as an eagle. The bird did not grow. It did not gain a single solid part. Its speed alone made it heavy. The quarks in a proton are those hummingbirds, and their blurring motion adds real weight to the whole. This is confirmed physics, measured and proven. Part of the proton's missing weight comes straight from the energy of the quarks racing around inside it. Their motion is not a small effect. It is a major slice of the 99%. So we can already name two sources filling the hole: the energy stored in the straining gluon field and the energy of the quarks moving near light speed. Both are pure energy. Both become weight. Both are running full blast inside every proton in your body while you sit there feeling perfectly still. Picture yourself right now. You feel motionless, calm, steady. Yet inside every one of your countless protons, quarks are screaming around at nearly the speed of light, and that violent inner motion is a huge part of the reason you weigh anything at all. You're built from stillness that is secretly pure motion. We are close to the full picture, but one piece of the strong force is still hiding. It is the reason the gluons can build up so much energy in the first place. Because gluons do something no other force messenger in the universe is willing to do, and it turns the strong force into a runaway monster. Every force has a messenger. Light carries a force too, and its messenger is the photon. Photons and gluons look like cousins on paper, both weightless, both zipping around, both carrying a force between particles. But gluons do one wild thing that photons never do. And that one difference is why the strong force becomes a monster. Photons ignore each other, send two beams of light crossing through the same spot and they pass right through, waving hello and moving on. Light does not grab light. Photons are loners. They carry the force between other things, and they leave each other completely alone. Gluons are the opposite. Gluons grab each other. A gluon flying through the proton can reach out and yank another gluon, pulling it in, tangling with it, sticking to it. The messengers of the strong force are sticky to their own kind. That single strange fact changes the whole game. Think about what that does. Photons keep the force from light calm and simple, because the messengers stay out of each other's way. But gluons pile onto each other, feeding the force, multiplying it, letting it build and build. Instead of a clean, gentle force, you get a wild, tangled, self-feeding storm. The strong force does not just carry itself between quarks, it reinforces itself, over and over, growing thicker and denser inside the proton. This is why the space inside a proton is so unbelievably crowded with energy. The gluons are not just three neat lines between three quarks, they are a churning web, gluons grabbing gluons, a dense knot of force filling every corner of the proton, and every strand in that web carries energy. Pile up enough of it, and you get the heaviness that outweighs the quarks 100 to 1. Picture two crowds of people. In the first crowd, everyone walks straight to their destination, politely ignoring everyone else, never bumping, never grabbing. That is light, calm, orderly, thin. In the second crowd, everyone grabs the people next to them, who grab the people next to them, until the whole crowd tangles into one thick heaving mass that fills the entire square. That is the strong force, a grabbing, growing pile-up of messengers that never stops feeding itself. This is confirmed, and it is the deep reason the strong force earns its name. The self-grabbing gluons make it the most powerful force in the everyday universe, strong enough to lock quarks in place forever, and to pack a proton with more energy than seems possible for something so small. It also sets up something almost unbelievable, a rule that flips everything you know about how forces behave. Normally, when you pull two things apart, the force between them fades. Move a magnet away from your fridge, and its pull gets weaker with distance. Every force in your daily life works this way. Farther apart means weaker pull. The strong force refuses to play by that rule. Because the gluons grab each other and multiply, something happens when you try to pull two quarks apart that has no match anywhere else in nature. The harder you pull, the stronger the force fights back. And that backward, impossible, seeming behavior is about to explain why no human has ever held a single quark and never will. Everything you know about forces says the same thing. Move away and the pull gets weaker. Walk away from a campfire and it warms you less. Pull a magnet off the fridge and the grip fades. Distance kills a force. That rule feels as certain as gravity. The strong force breaks it completely and in the most shocking way possible. With the strong force, pulling two quarks apart makes the force between them stronger. Farther apart means a fiercer grip, the exact opposite of everything else in nature. Sit with how strange that is. Try to drag two quarks away from each other, and instead of getting easier, it gets harder, and harder, and harder. The strong force digs in like a spring that tightens the more you stretch it, fighting you more viciously the farther you go. There is no escaping. The pull just keeps climbing. To understand why, go back to the gluons stretching between the quarks like tense rubber bands. When the quarks sit close, the bands are loose and the pull is gentle. But as you pull the quarks apart, you stretch those gluon bands, and stretching them stores more energy, which means more force. The band does not thin out and snap like a normal rubber band would. Because the gluons grab each other, the stretched region stays thick and strong, and the tension keeps rising the more you pull. Physicists picture it as a string or a tube of pure force running between the two quarks. Try to separate them, and you stretch this force tube longer and longer, pumping more and more energy into it the whole time. The tube never weakens, it only gains strength and energy as it stretches. Here is the mind-bending result. There is no distance far enough to break free. You could pull with all the energy in a lightning bolt and the quarks would still refuse to come apart, because the force just grows to match your effort. A single quark, alone, out in the open, has never been seen by any human being, not once in all of history. That has a name. Scientists call it confinement, because the quarks are confined, trapped, locked inside forever by a force that gets stronger the harder they try to escape. This is confirmed, one of the bedrock facts of the strong force. Quarks come in groups, always, sealed inside particles like the proton, and no known process can set a lone quark free. Picture trying to grab one end of a magnet. You want to hold just the North Pole by itself, so you cut the magnet in half. But cutting it does not give you a lonely North Pole. Each new piece instantly grows its own South Pole. No matter how many times you cut, you can never hold a North Pole alone. Quarks are like that. Nature simply will not let you have just one. So the strong force keeps the quarks prisoner, and in doing so it pours endless energy into the space between them. That energy becomes weight. The prison itself is heavy, far heavier than the prisoners inside. But this backward rule raises a wild question. If pulling the quarks apart pumps in more and more energy, and that energy has to go somewhere, then what happens when you pull really, really hard? The answer is nature performing a magic trick, conjuring brand new matter out of raw force, right before your eyes. Let us try the impossible. Let us try to rip one quark out of a proton and hold it up in the light, alone, so we can finally look at a single quark by itself. Physicists have chased this dream for over 50 years. Here is why it never works, and why it never will. Grab a quark inside a proton and start pulling. As you pull, you stretch that tube of strong force between it and its neighbours, pumping in energy, watching the pull grow stronger the farther you go. You strain harder. You pour in more energy. The force fights back tighter and tighter. You're winning ground, slowly dragging the quark away, feeding more and more energy into that stretched tube of force. Then, at some point, nature does something you never asked for. The energy in the stretched tube gets so high that it snaps, and the snap does not free your quark. Instead, all that trapped energy instantly turns into brand new matter. Out of the pure energy in the broken tube, a fresh quark and a fresh anti-quark pop into being right there in the gap. So you pulled a quark out hoping to hold it alone, and the universe answered by creating two new particles to fill the space. The new anti-quark rushes to your escaping quark and glues to it, forming a new particle. The new quark stays behind and patches up the proton. You end up with two particles instead of one lonely quark. You never get to hold just one. This is the golden rule striking again. Energy becomes matter. The energy you poured into stretching the force tube did not vanish. Einstein's equation ran backward, right in front of you, and turned your pulling energy into solid new quarks. You tried to isolate one quark and accidentally built more matter instead. Picture a bar magnet one more time. because it is the perfect match. You want a lonely north pole, so you snap the magnet in two. Instead of one free north pole, each half instantly sprouts a fresh south pole. Snap again, same result. Every cut makes a new pair of poles. You can chop forever and never ever hold a single pole alone. Quarks work exactly like this. Try to separate one and nature spawns new partners to keep it company. This is confirmed, seen countless times inside particle accelerators. When scientists smash protons together and try to knock quarks loose, they never see a bare quark fly out. Instead, they see sprays of new particles, each one a little bundle with its quarks safely sealed inside. The quarks are always dressed up in groups, never naked, never alone. So the strong force does two incredible things at once. It traps the quarks forever, and when you fight that trap, it turns your effort into brand new matter. The prison cannot be broken, and trying to break it only makes more prisoners. This constant creation of new quark pairs is not just a trick that happens when scientists pull. It is happening all the time, on its own, inside every proton, right now. The proton is not a calm home for three quarks. It is a place where matter is constantly flashing into being and vanishing again, a churning sea of particles appearing and disappearing faster than you can blink. And that boiling sea is the next piece of your weight. We just saw that pulling a quark apart spawns new quarks. Here is the twist that makes the proton even wilder. You do not have to pull anything. This creation of new particles is happening constantly on its own, inside every proton without anyone touching it. The strong force inside a proton is so powerful, so packed with energy, that it cannot sit still. Remember Einstein's rule, energy becoming matter? Well, there is so much energy crammed into the tiny space of a proton that the energy keeps spilling over into brand new particles all by itself. Quarks and anti-quarks flash into existence out of the raw force, exist for the shortest sliver of a moment, then vanish back into energy. Blink and you would miss 1 trillion of these flashes. New quark pairs appear, live for a heartbeat far shorter than a heartbeat, and disappear over and over endlessly, everywhere inside the proton. The proton is boiling. It is a churning, flickering storm of particles being born and dying faster than any clock could ever count. So the neat picture of three quarks sitting in a bubble was always a lie we told ourselves to keep things simple. The real proton holds those three main quarks, yes, but it also holds a frantic, ever-changing crowd of extra quarks and anti-quarks, popping in and out of being every instant. Scientists have a name for this churning crowd. They call it the sea, a sea of particles, boiling inside every proton in your body. Why does this matter? For weight. Because every one of those flashing particles carries energy, and energy becomes mass. The boiling sea adds its own share to the proton's heaviness. All that constant creation and destruction, all that flickering matter contributes to the weight you carry around. Part of you is made of particles that exist for less than an instant before winking out, replaced by new ones just like them. Picture the surface of a pot of water at a rolling boil. Bubbles form, rise, and burst. Thousands of them constantly, so fast the surface never holds still. No single bubble lasts, but the boiling itself never stops, and it fills the whole surface with churning motion. The inside of a proton is that boiling surface, except the bubbles are particles of matter, appearing and vanishing trillions of times faster than any bubble in any pot. This is confirmed, part of our deepest and most tested understanding of matter. The boiling sea inside the proton is real, measured through its effects, woven into every calculation that gets the proton's weight right. It is one of the strangest truths in science. Ordinary matter, the stuff of your body, is partly built from particles that flash into being and die in the blink of an eye. So now count up what fills the proton. 3 quarks, tiny and light. A dense web of grabbing gluons, weightless but bursting with energy. Quarks racing near light speed, their motion turning into weight, and a boiling sea of new particles, endlessly born and destroyed, Almost none of it is solid, steady stuff. Almost all of it is motion, force, and flickering energy. Which leads to a strange and beautiful conclusion about what a proton truly is at its core. Because when you finally add up everything inside, you realize the proton is barely made of matter at all. It is something far stranger and far more wonderful than a simple ball of 3 quarks. Let us go all the way inside the proton now and really live there for a moment, because the true picture is so far from the neat little diagram in a textbook that it feels like a different universe. Forget 3 tidy balls sitting in a bubble. That picture is a cartoon for beginners. The real proton is chaos. It is the busiest, most violent, most crowded place you could ever shrink down into, all packed into a space smaller than a speck of dust. Dive in, and here is what surrounds you. 3 main quarks darting around near the speed of light, blurring so badly you can barely track them. Between them, a thick, tangled web of gluons, grabbing each other, multiplying, stretching, snapping, filling every gap with straining force, and all through it, the boiling sea, a frantic storm of extra quarks and anti-quarks flashing into being and dying, trillions of times over, faster than any clock could tick. Nothing holds still, nothing rests. The whole place roars with motion and force and flickering energy, a furnace that never cools. This tiny core inside every atom of you is the wildest weather system in the universe, raging in a space too small to ever see. And here is the truth that all of this has been building toward. Add up what makes that furnace heavy, and almost none of it is solid matter. The 3 quarks contribute their tiny 1%. Everything else, the whole missing 99%, is energy. The energy of the straining gluons, the energy of the racing quarks, the energy of the boiling sea. Pure, weightless energy turned into weight by Einstein's equation running backward. So what is a proton, really? It is a tiny knot of trapped energy, wearing the costume of solid matter. It looks like a hard little ball from the outside, but inside it is almost pure force and motion, frozen into the shape of a particle. The heaviness you can measure on a scale is the heaviness of energy, locked in place by the strongest force in nature. Physicists gave this incredible idea a name that sounds almost like a riddle: mass without mass, weight built from things that have no weight of their own. It is one of the most beautiful phrases in all of science, because it captures the whole impossible truth in 3 words. The proton has mass. Its parts, deep down, have almost none. The mass comes from what the parts are doing, not from what the parts are. Sit with that. The most solid, dependable weight in your body, the weight of your bones and blood and every heavy thing about you, is really trapped energy pretending to be stuff. You are heavy because energy is heavy, and your protons are volts holding an unbelievable amount of it. This idea was so bold, so strange, that for a long time it was more of a beautiful theory than a proven fact. Scientists were confident the strong force made the protons weight. But confident is not the same as proven. They had the picture, they had the equations. What they did not have was a way to prove, beyond all doubt, that this boiling storm of energy really does add up to exactly 938. To settle it once and for all, they would need to do something almost unthinkable. They would need to build a proton from scratch, inside a machine, using nothing but the raw rules of the strong force, and see if the weight came out right. Before we watch scientists try to build a proton inside a machine, let us pull all the threads together, because the full picture of what you are made of has quietly become one of the most astonishing ideas you will ever hear. Start with your body on a scale. Say it reads 100 pounds. Every instinct tells you that weight comes from stuff. Solid, heavy material, packed into your bones and muscles. That is how weight has always seemed to work. The truth is stranger by a mile. Of that 100 pounds, only about 1 pound comes from the true, built-in weight of your particles, the little masses the Higgs field hands out to your quarks and electrons. The other 99 pounds are something else entirely. Pure energy, locked inside your protons, wearing the disguise of solid weight. Look at where that 99 pounds actually comes from, and every source is motion or force. The straining gluon field, packed with the energy of the strong force. The quarks racing around near the speed of light, their motion turning into mass. The boiling sea of particles flashing in and out of being, each one carrying its own energy. Not one of these is solid, steady stuff. Every single one is action, movement, trapped force. So here is the sentence that should change how you see yourself forever. You're almost entirely made of energy and motion, frozen into the shape of a person. The heaviness of your body is the heaviness of a storm, raging inside countless tiny cores, held in place by the strongest force in the universe. You're barely matter at all. You're mostly bottled lightning standing up and walking around. Feel how upside down that is. Right now, you feel solid, still, made of firm, dependable stuff. Yet the deepest truth of your weight is the opposite. Inside every proton in you, quarks scream around near light speed, gluons grab and multiply into a churning web, and matter boils in and out of existence trillions of times over. Your stillness is built from unimaginable motion. Your solidity is built from restless energy that never once stops moving. This is confirmed, woven into the most tested science we have. The weight of ordinary matter, the stuff of stars and oceans and mountains and you, comes overwhelmingly from energy, not from solid parts. It is one of the most profound facts humans have ever uncovered about the world, and hardly anyone outside of physics has ever been told, and it means that Einstein's famous equation is not some far-off rule that only matters for bombs and stars. It is written into your body, right now, in every atom. Energy became mass, and that mass became you. Every time you feel your own weight, you're feeling trapped energy pressing down, obeying the most famous line in the history of science. Still, a bold and beautiful idea is only worth as much as the proof behind it. For decades, this was the best theory scientists had, backed by strong evidence but never fully nailed down. To truly know beyond any doubt, they had to test it in the hardest way imaginable. They had to grow a proton out of pure math and force, inside one of the most powerful machines ever built, and see if its weight came out right. If it worked, it would prove that most of what you are is nothing but motion, force, and energy. And the machine they built to try it is where we go next. To prove that force and energy make almost all of your weight, scientists needed to build a proton from scratch and check its number against the real world. You cannot do that on a lab bench with tweezers. A proton is far too small and far too violent to assemble by hand. So they built one somewhere else, inside a computer. Here is the plan they came up with, and it is wild. Take the equations of the strong force, the rules for how quarks and gluons behave, and turn them into a giant calculation. Chop a tiny chunk of space into a grid of points, like turning smooth space into a video game world made of tiny cubes stacked in every direction. On that grid, place the quarks, fill the space between them with gluons, then let the rules run and watch what the strong force builds. If the idea is right, a proton should form on the grid all by itself. The quarks should lock together, the gluons should tangle into their churning web, the boiling sea should start to boil, and out of all that action a certain weight should appear. The machine would then tell you that weight, and you could check it against the real proton, against 938. There was a catch, and it was brutal. Remember that gluons grab each other, feeding the strong force until it explodes in power. That same feature makes the math a nightmare. Every point on the grid affects every other point, over and over in a tangle so dense that a normal computer would choke instantly. To handle it, scientists needed some of the most powerful supercomputers ever built, machines that fill entire rooms and gulp down enough electricity to power a town. Even those giants had to run for months. Billions upon billions of calculations grinding away day and night just to grow one proton out of pure rules and see how heavy it came out. It was like predicting the weather, except the storm being predicted was the storm inside a single particle smaller than a speck of dust. And they played fair. This is the part that makes the whole test honest. They did not sneak the answer in. They did not tell the computer the proton weighs 938 and ask it to agree. All they fed in were the basic rules of the strong force and the tiny weights of the quarks, the 2 and the 5 that the Higgs hands out. Nothing else, no hint of the final number. Then they let the machine calculate what the weight of a proton should be, starting from almost nothing. So the stage was set for one of the boldest tests in the history of science. On one side, decades of theory saying that force and energy create the missing 99%. On the other, a real proton with a real measured weight. And in the middle, a supercomputer grinding for months to see if raw rules, could grow the right answer. If the number came out wrong, it would mean we had misunderstood the deepest source of ordinary weight, and physicists would be sent back to the drawing board. If it came out right, it would prove something almost too strange to believe, that most of your body is built from nothing but force and energy. Everyone waited for the machine to finish, and when the final number finally appeared on the screen, it settled the question for good. The supercomputer finished its months of grinding. Out of the raw rules of the strong force, out of the grid and the gluons and the boiling sea, a number appeared. The weight of a proton, calculated from scratch, using nothing but the laws of nature and the tiny weights of the quarks. The number was right. It landed almost exactly on 938. The proton the computer grew from pure rules weighed the same as the real proton sitting inside every atom of your body. The match was so close that the small gap between them came down to the limits of the machine itself, not any flaw in the idea. The theory had passed the hardest test anyone could throw at it. Sit with what that actually means. Scientists started with almost nothing. 3 quarks with tiny weights, the plain rules of the strong force, and a computer. They did not tell it the answer, and out of those bare ingredients, a full proton formed with a full proton's weight. The missing 99% appeared out of the force and the energy, exactly as the theory had promised. The heaviness grew straight out of the action inside. This was the proof. Before, the idea that force and energy make your weight was a beautiful, well-supported theory. After, it was confirmed, locked in, shown to be true by growing a proton in a machine and watching its weight come out right. It stands today as one of the great triumphs of modern physics, and it was completed only in recent years, when computers finally grew strong enough to do the job. Feel how far we have travelled. We started by weighing a proton and finding its parts add up to only 1%. We hunted through the strong force, the weightless gluons, the racing quarks, the boiling sea, chasing the missing 99%. Every step said the same thing. The weight is energy, turned into mass by Einstein's equation. And now a machine has grown a proton from raw rules and confirmed it. The mystery has an answer, and the answer is real. So here is the truth, proven and solid. Almost all the weight of ordinary matter is created, not carried. It is not handed to the proton by some heavy ingredient inside. It is built, fresh, by the strong force straining to hold 3 restless quarks together, and by the energy of everything moving and boiling in that tiny space. Weight, manufactured out of pure action. Your body works this way. Every heavy thing about you is manufactured moment by moment inside your protons by a force you never feel and never see. You are heavy because a storm rages inside each of your tiny cores, and that storm has been running since before you were born, and it never stops, not even for a second. This idea is so strange that it changes how you should see everything around you. If the proton makes its own weight out of energy, then so does everything made of protons. Your desk, your phone, the ground under your feet, all of it, heavy for the same secret reason. And once you understand that a single proton is mostly bottled energy, a bigger thought arrives, because you are not the only thing built from protons. The entire visible universe is. Every star, every planet, every ocean follows the same rule, and that means almost all the weight in the cosmos is hiding the same secret. We have been talking about your body, but the secret of the proton reaches far past you. It fills the whole visible universe, because everything you can see, everything made of atoms, is built from protons, and every one of those protons plays the same trick. Look up at the night sky. Every star out there is a giant ball of atoms, mostly hydrogen, and hydrogen is just protons with tiny electrons. The sun alone holds more protons than you could count in 1 trillion lifetimes. And almost all the weight of the sun, the crushing, enormous mass that holds whole planets in orbit, comes from the same place your weight does, from the strong force and the energy locked inside all those protons. The sun is mostly bottled energy too, on a scale beyond imagining. Look down at the ground. A mountain feels like the heaviest, most solid thing there is. Millions of tons of rock, unmovable, ancient. Yet a mountain is made of atoms, and those atoms are made of protons, and those protons make almost all their weight out of trapped energy. The mountain, for all its bulk, is mostly force and motion frozen into stone. Its heaviness is the heaviness of countless tiny storms. Look at the ocean. Every drop of water is atoms, mostly hydrogen and oxygen, packed with protons. The entire weight of every sea on Earth, all that water pressing down miles deep, comes overwhelmingly from the strong force straining inside those protons. The ocean is a vast field of bottled energy, sloshing and rolling under the moon, so step back and take in the full size of this. Nearly all the ordinary weight in the entire universe, every star, every planet, every rock, every ocean, every living thing on every world that might exist comes from the same source. Force and energy, turned into mass by Einstein's equation, inside countless protons. The 1% handed out by the Higgs is a tiny garnish. The other 99% everywhere is manufactured by the strong force. Picture the whole universe on a giant scale. Add up the weight of everything you can see, all the galaxies, all the light of 100 billion stars in each one. Now ask where that weight comes from. The honest answer is that almost all of it is energy, dressed up as matter. The visible universe is not mostly stuff. It is mostly action, frozen into the shape of things. This is confirmed, the same proven physics that grew a proton in a supercomputer. It applies to every proton anywhere, so it applies to everything you have ever seen or touched or dreamed of visiting. The stars in the sky, the planets we hope to reach, the ground of distant worlds, all of it heavy for the same secret reason. It means the universe is far stranger than it looks. It looks solid, full of hard, weighty things. Underneath, it is a cosmos of trapped energy, held in the shape of stars and stone by the strongest force in nature. Reality is lighter than it seems, and heavier than it should be, both at once. But this raises a haunting question. If your weight is made of energy locked inside your protons, then where did that energy come from in the first place? Who filled these tiny cores with so much force? The answer takes us back to the very beginning of time, to a moment older than any star. If almost all your weight is energy trapped inside your protons, then a strange question follows you around. When did that energy get in there? Who filled these tiny cores? The answer reaches back to a time before the sun, before the earth, before a single star had ever shone. It reaches back to the birth of the universe itself. Wind the clock all the way back, not thousands of years, not millions. Back to the very first moments after the universe began, a time so early it makes the age of the oldest star look like yesterday. In that first sliver of a second, the universe was unimaginably hot and packed together, a fireball beyond any furnace. Here is the wild part. In that fireball, protons did not exist yet. It was too hot for them to form. The quarks and gluons that would one day build every proton were loose, free, racing through the young universe on their own, in a churning soup hotter than the centre of any star. For the only time in all of history, quarks roamed free, unbound, out in the open. Then the universe did what hot things do. It expanded, and it cooled. And as it cooled past a certain point, in a flash near the very start of time, the loose quarks got caught. The strong force reached out, grabbed them in threes and locked them away inside brand new protons. Trillions upon trillions of protons formed all at once, all across the young universe, each one snapping shut around its three quarks. And in the instant those protons formed, their weights switched on. The strong force began straining to hold the quarks, the gluons began tangling into their web, the boiling sea began to boil, and all that energy became mass. In that first moment, the weight of ordinary matter was born. The heaviness of every star and world that would ever exist was set, right there, at the dawn of time. So here is the truth about the energy inside you. It is older than the stars, older than the galaxies. The protons in your body formed in the first moments of the universe, and the storm of energy inside them has been running, without a single pause, ever since. For billions upon billions of years, through the birth and death of countless stars, through the making of the Earth, that storm never stopped. Think about where those protons have been. Some of the protons in your hand right now formed at the beginning of everything, drifted through the young universe, got swept into a cloud of gas, pressed into a star, blasted out again, wandered through space, and finally settled into you. The energy inside them is the same energy that switched on at the birth of time. You're carrying a piece of the first moments of the universe, right now, in every atom. This is confirmed by our best understanding of the young universe, backed by what we see in the sky and what we can recreate for tiny instants in our biggest machines. The story of your weight is the story of the cosmos itself, written into particles that are as old as time. So your weight is ancient, and it is energy, and it is proven. Yet a proton is not quite alone in the atom. It has a close cousin, almost its twin, sitting right beside it. And the tiny difference between them turns out to be the reason you get to exist at all. A proton has a twin. It lives right beside it, in the heart of almost every atom, and at a glance the two look nearly identical. The twin is called the neutron, and the tiny difference between them is one of the most important facts in the universe. Remember what makes a proton: 2 up quarks and 1 down quark, held by the strong force. The neutron is almost the same recipe, with 1 swap: 1 up quark and 2 down quarks. Trade an up for a down, and a proton becomes a neutron. That single swap is the only real difference in their guts. Because the recipes are so close, the neutron weighs almost exactly what the proton weighs. Almost. The neutron is just a whisker heavier. Remember, the proton weighs about 938 in our units. The neutron weighs about 940, a gap of less than 2. Out of nearly 1,000, the two twins differ by less than 2. That is one of the tightest matches in all of nature. Where does that tiny gap come from? Partly from the Higgs, because a down quark is a touch heavier than an up quark, and the neutron carries an extra down. And partly from the electric charge the quarks carry, which nudges the numbers a hair. Add it up, and the neutron ends just barely on the heavy side. A whisker of weight, and no more. That whisker sounds too small to matter. It is one of the most important numbers in existence. Here is why. In physics, heavier things tend to be less stable. They like to shed weight and turn into something lighter if nature allows it. Because the neutron is a whisker heavier than the proton, a lone neutron floating by itself is unstable. Left alone in empty space, a single neutron survives for only about 15 minutes on average, then breaks down and turns into a proton, spitting out a couple of light particles as it changes. This is confirmed, measured over and over. A free neutron does not last. The proton is the opposite. Because it is the lighter twin, a lone proton has nothing lighter to fall into. It has nowhere to go. So a proton, left completely alone, stays a proton. It sits there, stable, seemingly forever. The whisker of weight that makes the neutron crumble is the same whisker that makes the proton rock steady. Feel how delicate this is. The universe balanced two twins on a knife edge and made the proton the lighter, sturdier one by the tiniest possible margin. If that margin had tipped the other way, everything would be different. And when you look at what that difference protects, you realize this whisker is standing guard over your entire existence. Because the proton is the particle that makes ordinary matter possible. It is the core of hydrogen, the most common atom in the universe and the fuel of every star. It is the anchor of every atom in your body. A stable proton is the foundation that everything else is built on. Knock it loose, and the whole structure comes down. So a razor-thin gap in weight, set at the birth of the universe, decides whether stable atoms can even exist. That is a lot resting on almost nothing. And to see just how much, imagine flipping that tiny gap the other way and watching what happens to the universe. Let us play the most dangerous game in physics. Let us reach into the universe and flip that tiny gap between the proton and the neutron. Make the proton the heavier twin instead of the lighter one. Just a whisker of change. What happens? Everything falls apart. Start with the proton itself. Right now it is stable because it is the lighter twin, with nothing to fall into. Flip the gap, and suddenly the proton becomes the heavier one, the unstable one. Now a lone proton wants to crumble. the way a lone neutron does today. It would break down and turn into a neutron, shedding weight to reach the lighter state. The steady anchor of every atom would become a ticking clock. Now think about hydrogen. A hydrogen atom is one proton with one electron. In our flipped universe, that lonely proton at the center would decay. It would grab its own electron, turn into a neutron, and the hydrogen atom would simply cease to be. Every hydrogen atom in existence would vanish, one by one, transformed into bare neutrons drifting alone. Lose hydrogen, and you lose almost everything. Hydrogen is the most common atom in the universe. It is the main fuel that stars burn. It is 1/2 of every water molecule. It is woven through the fats and sugars and proteins of every living thing. Erase hydrogen, and stars cannot shine the way they do. Water cannot form. The chemistry of life has nothing to build with. So in a universe where that tiny gap is flipped, there are no stable hydrogen atoms, no oceans of water, no ordinary stars burning steadily for billions of years, and no living things made of the molecules we're made of. There would be no you. There would be no one at all to notice the difference. The whole warm, watery living world would never happen, and the flip needed to cause all this is unbelievably small. A shift of less than 2 out of nearly 1,000. A change so slight you might round it away by accident. Yet that tiny margin is the difference between a universe full of stars and life and a universe of drifting, lonely neutrons where nothing interesting ever forms. This is confirmed reasoning built on the same solid physics we have followed the whole way. The stability of the proton really does hang on that whisker of weight, and that whisker really is set by the strong force, the quark weights, and the electric charges inside. Change the recipe by a hair, and the universe becomes barren. Here is the thought that should give you chills. The very same strong force that makes almost all your weight also, through this delicate balance, makes your existence possible in the first place. It builds the heaviness of matter, and it sets the razor-thin gap that lets stable atoms survive. 2 jobs, 1 force, and both of them had to come out just right for you to be here. So the proton is stable, and its stability guards all of life. But that word, stable, hides a deeper question that has haunted physicists for decades. We say the proton lasts forever. Does it, really? Or does even this rock-steady particle, the anchor of all matter, secretly carry a tiny crack, a slow doom ticking away too quietly to see? We keep saying the proton is stable, steady. It lasts, seemingly, forever. But that word forever hides one of the biggest open questions in all of physics. Does a proton truly last forever? Or does it someday, in the deepest depths of time, finally break apart and die? Nobody has ever seen a proton decay, not once, in all the years scientists have watched. As far as anyone can tell, a lone proton just sits there, stable, unchanging, for as long as you care to wait. That is the picture we have followed the whole way. Some theories whisper that this might be an illusion. These are big, ambitious ideas that try to tie all the forces of nature together into one grand rule, and several of them predict something unsettling. They say the proton is not truly immortal. They say it should very rarely break down and vanish, releasing its energy and leaving lighter particles behind. If they are right, then even the anchor of all matter carries a hidden crack. So scientists went hunting for a dying proton. Here is the problem. If protons do decay, they do it almost never. The predicted lifetime of a proton is so long, it makes the age of the universe look like a single tick. Our universe is roughly 14 billion years old. A proton, if it dies at all, might last a number of years so vast that you would have to write a 1 followed by dozens of zeros. Compared to that, the whole life of the cosmos so far is nothing. How do you catch something that rare? You cannot watch one proton and wait, because you would be waiting far longer than the universe has existed. So scientists use a clever trick. They gather a colossal number of protons in one place and watch them all at once. Deep underground, they build giant tanks holding thousands of tons of pure water, packed with more protons than you could ever count. With so many protons under watch, if even one of them happens to decay, sensitive detectors lining the tank should catch the flash. These experiments sit far below the surface, shielded by mountains of rock, watching in the dark year after year, waiting for a single proton to die. and so far, in all that watching, they have seen nothing. No proton has been caught breaking down. Every proton they have watched has stayed whole. That silence is powerful. It tells us the proton is even more stable than we can easily test. If it decays at all, it does so more rarely than the biggest experiments have been able to catch. The proton is the closest thing to immortal that ordinary matter has. It may outlast the stars, outlast the galaxies, outlast almost everything. So we are left with a genuine mystery, unsolved to this day. We do not know for certain whether the proton lives forever or dies incredibly slowly. Some of our deepest theories say it must eventually die. Every experiment so far says, if it does, we have not caught it yet. The question sits open, one of the great unanswered puzzles about the particle that makes up your world. And the strange thing is, the puzzle of the proton's weight is not the only mystery hiding inside it. There is a second secret in there, a second sum that refuses to add up, just like the weight did. It has to do with the way the proton spins. The proton has a second secret, and it echoes the first in a way that feels almost eerie. Just like its weight refused to add up from its parts, the proton's spin refuses to add up too. And for years, this second failed sum drove physicists to the edge of their patience. Every proton spins. That sounds simple, and it is one of the most basic facts about the particle. A proton behaves a bit like a tiny spinning top, carrying a fixed amount of spin that never changes. This spin is real, measured, and it matters enormously. It is the reason magnets work. It is the reason the machines in hospitals can peer inside your body to take detailed pictures. The spin of the proton reaches right into your daily life. So where does the proton spin come from? The obvious answer, the one everyone reached for first, sounds familiar. The proton is made of 3 quarks, and quarks spin too. So just add up the spins of the 3 quarks, and you should get the spin of the proton. Simple, clean, the way it ought to work. You can probably feel the trap coming because we have been here before. Scientists measured how much of the proton's spin comes from its quarks. They expected the quarks to supply all of it, or close to all of it. Instead, they got a shock. The 3 quarks account for only about 1/3 of the proton's spin, maybe less. The other 2/3 come from somewhere else entirely. When this result came out, it stunned everyone so badly that people gave it a dramatic name. They called it the spin crisis. The word crisis is strong for physics, but it fit. A basic, obvious sum had failed. The quarks, the things everyone thought carried the spin, only carried a slice of it. The rest was missing, unaccounted for, hiding somewhere inside the proton just like the missing weight had been. Feel the echo here. Twice now we have looked inside the proton expecting the 3 quarks to supply something basic. Twice the quarks have come up far short. The weight they barely provide. The spin they barely provide. It is as if the proton keeps telling us the same lesson, over and over. Do not trust the 3 quarks to explain me. The real action is somewhere else, and that somewhere else, once again, points to the storm inside, the gluons, the motion, the energy, the parts of the proton that carry no weight of their own but do almost all the real work. If the quarks only supply 1/3 of the spin, then the churning web of gluons and the swirling motion inside must supply the rest. The same hidden storm that makes the weight seems to make the spin as well. This is confirmed. The measurements are solid, repeated by different teams, and they all agree. The quarks alone cannot explain the proton's spin. That much is certain. What remains uncertain, what physicists are still working hard to pin down today, is exactly how the missing spin is divided up among everything else inside. So we have a second hunt on our hands, running right alongside the first. The missing spin has to be hiding somewhere in that boiling interior, and chasing it down leads to a picture of the proton's insides even wilder than the one we already have. 2/3 of the proton's spin is missing from the quarks, so where is it? To find it, we have to look at the same churning storm that made the weight, because the answer is hiding in the same place. Start with the gluons. Remember them, the weightless glue that holds the quarks together, tangling into a dense web inside the proton. Gluons do more than carry force. Gluons can spin too in their own way, and there are a huge number of them packed into that tiny space, so a big chunk of the proton's missing spin may come from the gluons themselves, all their little spins adding up inside the storm. Scientists have hunted for this gluon spin using enormous machines that smash particles together and read the debris. and they have found real evidence that the gluons do carry a meaningful share of the proton's spin. The weightless glue spins too. On top of holding the quarks together, it carries a real share of the proton's own spin. This part is measured and increasingly solid, though the exact amount is still being nailed down. But gluon's spin alone does not seem to close the gap. There is another source, and it is one you know from everyday life: motion in a circle. Think of a spinning carnival ride. The riders themselves might be sitting still in their seats, not spinning at all, yet the whole ride carries a spin because everyone is swinging around the centre. That circling motion is its own kind of spin. The same thing happens inside the proton. The quarks and gluons stay in constant motion. They are swirling, orbiting, circling around inside the tiny space, moving in great looping paths. And all that swirling motion carries spin, the same way the carnival ride does. So part of the proton's missing spin is hidden in the orbital motion, the endless circling of everything inside. Put it together, and the picture is dizzying. The proton's spin comes from a mix: a slice from the quarks spinning, a slice from the gluons spinning, a slice from everything swirling and orbiting inside. Add those slices up, and they should finally reach the full spin of the proton. Scientists are still measuring each slice carefully, still working to make the pieces add to the whole with confidence. The full accounting remains an open, active puzzle right now. Feel how this rhymes with the weight. The proton's weight came from the quarks plus the gluons plus the motion, all working together, with the quarks supplying only a sliver. Now the proton's spin looks the same: quarks, gluons and motion, all pitching in, with the quarks supplying only a portion. The same wild, crowded storm inside the proton is doing double duty, making both its weight and its spin. This is one of the biggest reasons scientists are so hungry to look deeper inside the proton. They want to map exactly how the spin is shared out, slice by slice, and finally close the sum. The weight puzzle got solved by a supercomputer. The spin puzzle is still being cracked, out on the front lines of physics today. And spin is not the last surprise waiting in there. The boiling sea inside the proton, that storm of particles flashing in and out of being, hides an oddity of its own. Because when scientists looked closely at the sea, they found it was strangely lopsided, in a way no one had ordered. Return to the boiling sea inside the proton, that churning storm of quarks and antiquarks, flashing into being and vanishing again. For a long time, scientists assumed the sea was fair, balanced, even-handed. But when they looked closely, they found something odd. A lopsided tilt that nobody had ordered and nobody could fully explain. First, a quick reminder. The sea is full of matched pairs. A quark pops into being alongside its opposite, an anti-quark, and the two vanish together a moment later. There are different kinds in there. Up quarks and their opposites, called anti-up. Down quarks and their opposites, called anti-down. And the simple expectation was that the sea would hold about the same amount of each kind of anti-quark. Fair and balanced, no favourites. That expectation was wrong. When scientists carefully counted the anti-quarks in the sea, they found more anti-down than anti-up. The sea is lopsided. It plays favourites, holding a clear surplus of one kind over the other. This is confirmed, measured in careful experiments, checked and rechecked. The tilt is real. That might sound like a small technical detail, and in a way it is. But it is also a genuine puzzle, because there is no obvious reason the sea should lean one way. If the sea were just random pairs boiling up out of pure energy, you would expect it to stay even. Something is nudging it, tilting the balance, and the full story behind that nudge is still not completely understood. Scientists have ideas. One leading picture involves the proton briefly spitting out and swallowing tiny particles inside itself, a kind of inner reshuffling that could favour one type of anti-quark over the other. This picture explains part of the tilt and lines up with a lot of the data, but it does not seem to explain everything cleanly, and the exact reason the sea leans the way it does remains an open question. Fresh experiments in recent years have measured the lopsided sea more precisely than ever, and they have deepened the puzzle rather than closing it. Feel what this tells you about the proton. Even the boiling sea, the most chaotic, flickering part of the whole storm, is not random. It has structure. It has a preference. It tilts in a specific direction for reasons we are still chasing. The deeper we look into the proton, the more hidden order and hidden mystery we find, layered one inside the next. A thing that seemed like pure chaos turns out to keep careful, lopsided books. This is the pattern of the whole story. Every time scientists thought they understood the proton, a closer look revealed another surprise. The weight did not add up, the spin did not add up. And now, even the C, when counted carefully, comes out strangely lopsided. The proton keeps refusing to be simple, so here we have three mysteries braided together inside one tiny particle. Where its weight comes from, now solved. Where its spin comes from, still being cracked. Why its inner C leans lopsided, still open, and believe it or not, there is yet another puzzle waiting, one so basic it is almost embarrassing. For a while, scientists could not even agree on how big a proton is. Here is a puzzle so basic it sounds like a joke. For years, the smartest physicists on Earth could not agree on a simple question. How big is a proton? How wide is it across? You would think we settled that ages ago. We did not, and the fight over it shook the field. For a long time, scientists thought they had the proton's width pinned down. They measured it using ordinary hydrogen, that simplest atom of one proton and one electron. By studying how the electron behaves as it circles the proton, they could work out the proton's size. Team after team did this, and they landed on a number they trusted. The proton's width was settled, or so everyone believed. Then, around 15 years ago, a clever group tried a new method, and it broke everything. Instead of an ordinary electron circling the proton, they built a special version of hydrogen using a heavier cousin of the electron. This heavier particle circles much closer to the proton, so it feels the proton's size far more sharply. It should have given the most precise measurement of the proton's width ever made, the most trustworthy number yet. The number came out wrong, or rather, it came out different. The new, sharper method said the proton was noticeably smaller than everyone had believed. The gap between the old answer and the new one was small in absolute terms, but it was far too big to be a mistake. Two careful methods, two solid answers, and they flatly disagreed about the size of the most basic particle in matter. This kicked off what people called the proton size puzzle, and it was a real crisis. Think about how unsettling it was. We had grown a whole proton in a supercomputer and gotten its weight exactly right. We understood the deepest source of its mass, and yet we could not confidently say how wide the thing was. Two trusted measurements pointed at two different numbers, and nobody knew which to believe or why they disagreed. For years, scientists chased the problem hard. Was one method flawed? Was there some subtle mistake hiding in the old measurements, or the new ones? Or was nature trying to tell us something strange, some brand new physics lurking in the gap? The disagreement forced physicists to recheck their tools, their math, and their assumptions, right down to the foundations. Slowly, the crisis eased. Newer and better measurements, using improved methods, began lining up. And more of them leaned toward the smaller size, the one the heavier cousin of the electron had pointed to. The evidence now tilts strongly toward the proton being that bit smaller than the old number said. The fight has mostly cooled, and the smaller width has largely won out, though physicists still study it closely to be sure the story truly holds together. Look at what this episode reveals. Even the simplest question about a proton, how big it is, turned out to be a knife fight at the edge of what we can measure. The proton guards its secrets fiercely at every level, from its deepest source of weight down to the plain matter of its width. And there is one more layer to peel back, maybe the strangest of all, because to truly understand the proton, we have to understand the empty space around it, and it turns out empty space is not empty at all. To finish understanding the proton, we have to understand the emptiness around it, and here waits maybe the strangest idea in this whole journey. Empty space is not empty. What we call the vacuum, the perfect nothing between particles, is secretly full, humming with hidden activity beneath everything you see. Picture the emptiest place you can imagine. Deep space, far from any star, a stretch of pure void with no atoms, no light, nothing at all. You would call that empty. Physicists would tell you it is bursting with hidden life, because at the deepest level that vacuum is filled with invisible fields, and those fields never truly go quiet. They ripple, they flicker, They are always faintly active, even in perfect emptiness. Remember the Higgs field from earlier, that invisible substance spread through all of space, dragging on particles to give them weight. That field is everywhere, even in the emptiest void. So even in perfect nothing, the Higgs field is present, humming quietly, ready to grab any particle that passes through. Empty space already carries that hidden ingredient. The strong force has its own version of this, and it is wilder. The vacuum, the supposed nothing, is actually filled with a faint, ever-present froth of quarks and antiquarks flickering in and out of being. The same boiling sea we found inside the proton also churns, more quietly in empty space itself. Nothingness is gently boiling, everywhere, all the time. This is confirmed, woven into our deepest and most tested physics, and this hidden froth in the vacuum plays a real role in the story of mass. The constant flickering of the strong force in empty space is tangled up with how quarks get their properties in the first place. In a strange way, the emptiness around a proton and the storm inside it are part of the same deep system. The vacuum is not a passive stage where particles perform, it is an active player shaping the very things that move through it. Sit with how upside down this is. We started this whole journey thinking weight comes from solid stuff. Now we find that even empty space is not empty, that the void itself hums with hidden fields and flickering particles, and that this humming helps set the rules for mass. The deeper we go, the more the line between something and nothing blurs away. What looks like empty space is a churning ocean we simply cannot see. This is one of the most profound ideas in all of science, and it reaches far past the proton. It means the universe has no true emptiness anywhere. Every corner of space, no matter how remote, is filled with active fields, quietly shaping reality. The nothing between the stars is a something. The void inside every atom is alive with hidden motion. So the proton does not float in a dead, empty stage. It sits inside a humming, active vacuum, a nothing that is secretly a something, and the two are woven together at the deepest level we can reach. We have come a very long way. We have solved the mystery of the proton's weight, watched it confirmed in a supercomputer, and traced it out to the stars and back to the birth of time. Yet for all we have learned, the proton still holds secrets we cannot fully explain. And it is worth being honest about exactly where our knowledge runs out. We have solved a great deal on this journey. The weight of the proton, once a total mystery, now has a proven answer. But it would be a lie to pretend we understand the proton completely. We do not. And the honest edge of our knowledge, the place where the answers run out, is one of the most exciting frontiers in all of science. Let us gather up what still puzzles us, because the list is real and it is deep. We have solved where the proton's weight comes from, yes, that much is locked in. Yet all around that solved question, mysteries remain. We still cannot fully account for the proton's spin. We know the quarks supply only a slice, and that the gluons and the swirling motion supply the rest, but pinning down each slice exactly and making them add cleanly to the whole is still unfinished work. Scientists are chasing it right now, in labs around the world. We still cannot fully explain why the boiling sea inside the proton is lopsided, why it favours one kind of anti-quark over another. We have partial pictures, but no complete settled answer. The tilt in the sea remains an open question. We still do not know for certain whether the proton lives forever or dies unimaginably slowly. Some of our grandest theories say it must eventually decay. Every experiment so far has seen it stay whole. That question sits wide open, waiting. And there are deeper puzzles underneath all of these. We understand how the strong force makes weight, but the strong force itself, with its gluons grabbing gluons and its impossible backward rule, is fiendishly hard to calculate. We can grow a proton in a supercomputer, but only with months of grinding. There is no simple formula, no clean shortcut, that lets us predict everything about the proton with pencil and paper. The math is a jungle, and we have only cut a few paths through it. Even the vacuum, that humming hidden ocean of empty space, holds mysteries about how mass truly takes root. The link between the froth in the void and the properties of the quarks is real, but it is not fully mapped. There are corners of this picture where our best theories go quiet and our measurements struggle to reach. So the proton, the most common building block of ordinary matter, the thing inside every atom of you, is still not fully understood. We have cracked its greatest secret, the source of its weight. But it guards other secrets still, and some of them may take generations more to unlock. This is what makes the proton so thrilling to study. It sits at the exact edge of human knowledge. Look at it one way, and it is completely solved, its weight proven to the last decimal. Look at it another way, and it is a frontier, packed with open questions that could reshape physics when they finally fall. And scientists refuse to stop at this edge. To push past it, to see the missing spin and the lopsided sea and the deep workings of the strong force directly, they are building something new. A machine unlike any before it, designed for one purpose. To look inside the proton more clearly than anyone in history ever has. To conquer the puzzles still hiding in the proton, scientists are building a brand new machine, one designed for a single grand purpose: to peer inside the proton more sharply than any tool in history and finally map the storm within. Think about how hard it is to see inside a proton. It is smaller than a speck of dust, packed with quarks racing near light speed, tangled gluons, and a boiling sea. You cannot photograph it. You cannot hold it still. The only way to explore it is to fire tiny probes straight into it and read what bounces out, like mapping a dark cave by throwing pebbles and listening to the echoes. Older machines did this and taught us most of what we know. But to crack the remaining mysteries, the spin, the lopsided sea, the exact structure inside, scientists need probes far sharper and more controlled than ever before. So they designed a new kind of collider, a huge ring of tunnels where two streams of particles are whipped up to enormous speed and steered into each other with incredible precision. Here is what makes this machine special. It is built to send in a clean, precise probe and slam it into protons over and over from every angle at many different energies. Each collision reveals another tiny piece of the inside. Gather millions upon millions of these collisions, and scientists can slowly build a detailed three-dimensional map of what a proton truly looks like within, where the quarks sit, where the gluons crowd, how the spin is shared, how the sea churns and tilts. It would be the closest thing to a photograph of the inside of a proton that humans have ever made. A real map of the storm, drawn from millions of gentle collisions, showing the churning interior in a detail we can barely dream of today. The questions that have stumped physicists for decades, the missing spin, the lopsided sea, could finally meet their answers inside this machine. The plan is real and moving forward. Scientists have chosen where to build it, gathered teams from around the world, and begun the enormous work of making it real. A machine like this takes many years and huge effort to construct, but it is coming. When it switches on, it will open a new window into the proton and through it, into the deepest source of ordinary matter. Think about what that means for everything we have chased. We solved the weight with a supercomputer, growing a proton out of pure rules. Now, with this new machine, scientists aim to solve the spin and the sea by looking straight inside a real one. Theory and experiment, closing in on the proton from both sides at once, hunting down the last of its secrets. And whatever this machine finds, one lesson already seems certain. The proton will keep surprising us. Every time we have looked deeper, it has shown us something stranger, richer, and more full of hidden order than we expected. There is every reason to think the new machine will do the same, revealing wonders inside the proton that no one has yet imagined. So the hunt goes on, at the very edge of what humans can build and measure. But even now, before that machine reveals its secrets, we already know enough to say something astonishing about ourselves. Something that pulls this entire journey together into one final staggering truth. We have travelled from the surface of your skin down into the heart of a single proton, out to the stars and back to the birth of time. Before the last truth, let us put the whole recipe of you together, every ingredient in one clear picture. Because when you see the full accounting, it is stranger than any story. Start with your weight on a scale. Say it reads 100 pounds. That number has two sources, and only two, and now you know them both. The first source is the Higgs, that invisible field, humming through all of space, drags on your quarks and electrons and gives them their built-in weight. This is the famous one, the God particle from the headlines, the Nobel Prize winner, and its share of you is about 1 pound out of 100, 1%, real, important, and tiny. Without it, the delicate balance that keeps your proton stable would collapse, and atoms could not exist. So that 1 pound is precious, but it is only 1 pound. The second source is the strong force, and it supplies almost everything else. The straining gluon field packed with energy, the quarks racing near light speed, their motion turned to weight, the boiling sea of particles flashing in and out of being, all of that converted into mass by Einstein's equation running backward. This is the 99 pounds, the overwhelming bulk of you manufactured by a force with no fame, no headlines, no city-size machine built to celebrate it. Put the two together and you have the complete recipe. 1% from the Higgs, giving your smallest pieces their tiny weights. 99% from the strong force, building the rest out of pure trapped energy. That is the entire source of your heaviness, proven by measurement and confirmed by a supercomputer that grew a proton from scratch and got the number right. Now feel the strangeness of that recipe. The part everyone has heard of, the Higgs, does almost nothing to your total weight. The part almost no one has heard of, the strong force turning energy into mass, does nearly all of it. The famous answer is the footnote. The unknown answer is the whole book. And look at what the 99% really is, not solid stuff. Force, motion, energy. The heaviness of your body is the heaviness of a storm raging inside countless tiny cores, running without pause since the first moments of the universe. You are barely made of matter in the way you always pictured. You are mostly made of action, held in the shape of a person. This is the honest accounting of what you are, down to the deepest level science can reach. 1 pound of stuff given weight by an invisible field. 99 pounds of trapped energy, ancient as the cosmos, held together by the strongest force in nature. That is the recipe. That is you. We have found the answer we came for. We know where your weight comes from. All of it. Both the famous sliver and the hidden bulk. All that remains is to say the final truth out loud, plainly, the one line this entire journey has been building toward. Because once you truly understand where your weight comes from, you can never look at yourself, or anything around you, the same way again. Here is the truth this whole journey has been building toward, and it is one of the most astonishing facts a human being can know about themselves. Most of what you are is motion, force, and energy, not stuff, not solid, heavy material packed into your bones. Look at the deepest source of your weight, and you find almost no matter there at all. You find a storm, quarks racing near the speed of light, gluons tangling into a churning web, a sea of particles boiling in and out of being trillions of times over. All of it energy, frozen by Einstein's equation into the shape of a body. You are, at your core, bottled lightning that learned to stand up and think. Trace it back and every piece confirms this. We weighed a proton and found its parts add up to 1%. We hunted the missing 99 and found the strong force, straining to hold 3 restless quarks, pouring energy into a space smaller than a speck of dust. We watched a supercomputer grow a proton from raw rules and land on exactly the right weight. We followed that energy out to the stars and back to the first moments of the universe. Every road led to the same place. Your weight is manufactured moment by moment out of pure force, and this is true of everything you have ever seen. The chair you sit in, the ground under your feet, the mountains, the oceans, the stars scattered across the night sky. All of it made of protons, all of it heavy for the same secret reason. The universe looks solid, dependable, full of weighty things. Underneath, it is a cosmos of trapped energy, held in the shape of matter by the strongest force in nature. Reality is far stranger than it appears. The energy inside you is ancient beyond imagining. It switched on in the first sliver of a second after the universe began, when the strong force reached out and locked loose quarks into brand new protons. That storm has run without a single pause ever since, through the birth and death of countless stars, through the making of the Earth, all the way to this moment, inside you. You carry a piece of the dawn of time in every atom, and the proton still guards secrets we have not cracked. its spin not fully explained, its lopsided sea still a puzzle, its true immortality still unknown. Scientists are building new machines right now to look deeper, and there is every reason to believe the proton has wonders left, to show us that no one has yet imagined. But the greatest wonder may be the one you already hold. You feel solid, steady, made of firm, dependable stuff. Yet the deepest truth of your body is the opposite. You're a standing storm of energy, older than the stars, held together by a force you never feel and never see, obeying the most famous equation in all of science with every pound you weigh. So the next time you feel your own weight, the pull of the ground, the heaviness of your own body, remember what it really is. It is energy, ancient and immense, trapped inside you and pressing down. It is the universe, folded into the shape of a person, briefly awake and looking back at itself. Most of what you are is motion, force and energy, and now you know why.